In the previous module, we have studied continuous functions. In this module, we will study homeomorphisms. So, what is homeomorphisms? In group theory or in function analysis, we have studied various kinds of structure preserving mappings. For example, in group theory, we have studied isomorphism. In function analysis, we have studied linear isometry. For metric spaces, we have studied isometry. All these are structure preserving mappings. That is, if two structures have same properties, then they will be preserved by this type of mappings. For topological spaces, structure preserving mappings are homeomorphisms. Homeomorphism can be described in this way that two topological space will be homeomorphic if one can be transferred to another continuously and can be returned back also continuously. We will give the formal definition. And a property of a topological spaces or a property of a mathematical structure will be called topological property if it is preserved under homeomorphism. After homeomorphism, we will study topological spaces in two ways basically. One way will be study of various topological properties of topological spaces. This will be one kind of study. Another kind of property will be that whether two topological spaces are homeomorphic or not. Homeomorphism will help us to distinguish two topological spaces. For example, in this way, so let X and Y be two topological spaces and P be a topological property which is possessed by X, but that does not possess by Y. Then X and Y will not be homeomorphic. We will come back it formally. So, let us start slide presentation. In studying group theory metric space, we have observed structure preserving mappings such as isomorphism, isometry. In this module, we will discuss structure preserving mappings of topological spaces. So, let us give the formal definition of homeomorphism. Let X and Y be two topological space. By a homeomorphism f from X to Y, we shall mean a continuous function f from X to Y such that its inverse exists from Y to X and inverse is also continuous. That means there exists a continuous function g from Y to X such that g compose f is equal to identity mapping on X and f compose g is equal to identity mapping on Y. That means f transform X continuously to Y and g pull back Y continuously to X. Clearly, here G actually is F inverse. So, if O is an open set of X, then the inverse image of O under F inverse is the same as the image of O under the map F. The same thing happens in the case of closed sets. So, we can define a homeomorphism in the following way. A mapping f from X to Y between two topological spaces is a homeomorphism if and only if it is continuous and open or closed. Proof. Of course, the mapping should be continuous and bijective mapping. Proof. Since f is a homeomorphism, there exists some g from Y to X such that g compose f is equal to identity mapping on X and f compose g is equal to identity mapping on Y. This follows from the definition. This means that f of u is equal to z inverse u. Since g is a continuous mapping from Y to X, so z inverse u is open. That means f of u is open, hence f is an open mapping. Similarly, we can prove that if a mapping is continuous, bijection and closed, then that is also a homeomorphism. The following picture gives the clear idea about this. Now, let us produce some examples of homeomorphisms. Let f from R to R be defined by fx is equal to ax plus b, where a not equal to 0. This is an example of homeomorphisms. In fact, if we define gy is equal to fy minus b by a, then G gives the inverse mapping of f. Continuity is clear. If we observe clearly the mapping f, so what does f? There is two parts. One is multiplication of a by x, that means it increases or decreases the magnitude, and another part is plus b, that is fx is an affine transformation. So, this gives just the translation. So, we know that magnification and translation, both these two are continuous mapping. So, this type of mapping ax plus b always continuous mapping, and its inverse is also continuous. Let us produce another example of homeomorphisms. Let 0, 1 and 3, 4 be two open intervals. So, we get a homeomorphism between 0, 1 and 3, 5 in the following way. Let us put fx is equal to ax plus b. Now, we can choose a and b suitably such that 0, 1 map to 3, 5 open interval homeomorphically. This example shows that R and 0 infinity are homeomorphic. In fact, if we define f from R to 0 infinity by fx is equal to exponential function of x, then the graph of fx is the given in the picture. From this graph, it is clear that the mapping f is a homeomorphism. Let us produce another example. This example shows that unit square and unit circle are homeomorphic. So, this is the basically radial projection. From the picture, from the given picture, it is clear that we map a point on the square radially to circle, and in that way we can go back to the square. So, this is another example of homeomorphisms. Next, this example gives a homeomorphism within an open ball and whole Euclidean space. Let us consider Rn and its subset Bn, where Bn is the set of all x belongs to Rn such that magnitude of x is strictly less than 1. That means it is an open solid unit ball. In R2 it will be a disk, in R3 it will be an open solid ball. In general Rn, we will say that this is an open ball. Now, if we define a map f from Bn to Rn by fx is equal to x by 1 minus mod x, then this gives a homeomorphism from Bn to Rn. In fact, the mapping G from Rn to Bn defined by Gx is equal to x by 1 plus mod x is a continuous inverse of f. There is no question about the continuity of f and g, they are surely continuous. Let us put another example. S2 is called sphere. S2 is the subset of R3 consisting of all points whose magnitude is equal to 1. That is, S2 is equal to all x belongs to R3 such that norm of x is equal to 1. And let us consider C as equal to all x, y, z such that maximum of x, y, z is equal to 1. So, this is the square, unit square. We define the radial projection from C to S2 by the mapping f of xyz is equal to xyz by norm of xyz, that is root over x square plus y square plus z square. So, this mapping radially projects a point from C onto S2. Now, its continuous inverse is given by G, where G of xyz is equal to xyz by maximum of mod x mod y mod z. So, this gives the inverse of f, hence f is a homeomorphism, that means unit square and unit sphere, these two are homeomorphic. So, this is an important example throughout the study of topology, which shows that not every continuous bijective mapping is a homeomorphism. We define the mapping from semi-open interval 0, 1 to S1, where 0 closed, 1 is open and S1 is the unit circle. Now, mapping is defined by Px is equal to e to the power 2 pi I x. What does this mapping do? This mapping wraps the unit circle by the unit interval single time. So, in the previous example, we have produced an example of a continuous bijective mapping which is not a homeomorphism. The mapping is defined from semi-open interval 0 to 1 to the unit circle S1. This is defined by E of x is equal to e to the power 2 pi I x. So, why it is not an open mapping? If we consider 0 closed and say 1/4 open, so 0 to 1/4, this set, this interval is an open set in the semi-open interval 0, 1 in the subspace topology induced from the topology of R. Now, its image is the arc from 0 to upper half north pole of the circle, but the point, this is closed, but the upper half north is open. So, this arc is not an open set in S1. So, that means the mapping E from 0, 1 to S1 is not open, hence this is not a homeomorphism. Our next example is called stereographic projection. In fact, it gives a homeomorphism between a punctured sphere to the Euclidean space. To be more specific, let Sn be the n-dimensional sphere, all x belongs to Rn such that norm of x is equal to 1. Taken with the subspace topology from Rn plus 1, we claim that removing a single point from Sn gives a space homeomorphic to Rn. Which point we remove is irrelevant because we can rotate at any point of Sn into any other. For convenience, we choose to remove the north pole, that is the point 0, 0, 0, 1. Now, the set of points of Rn plus 1 which have 0 as their final coordinate when given the induced topology is clearly homeomorphic to Rn. It will be clear to you if you think in R2. So, if we take in R3 all points with the final coordinate 0, we get the plane R2. We define the homeomorphism from deleted sphere to Rn as follows. We define H from Sn minus n to Rn, which is called stereographic projection, as this. If x belongs to Sn minus n, then Hx is the point of intersection of Rn and the straight line determined by x and n. That means we take the line segment joining x to n and increase it, so that when it intersects Rn, that point will be the image of H. Now clearly H is bijective. Now let O be an open set in Rn. We construct a new set U in Sn, whose points are the points of intersection of the straight line segments which start at N and pass through the points of O. Expect the point N. See the diagram in the next page. Then O is open in Sn, but H inverse O is precisely the set U. Therefore, H inverse O is open in Sn minus n. These establish the continuity of H, and precisely similar argument deals with H inverse. That means by the similar argument we can show that H is also open mapping. Therefore, H is a homeomorphism. The picture is like this. So, here we have considered the set U and the set of intersection of the line segments from N to points of U on the sphere. Now, as we have claimed that, we formally define topological property. Definition: a property, say P, of a topological space is said to be a topological property if whenever two topological spaces X and Y are homeomorphic and one possesses the property P, then other will possess also the property P. Let us consider the following example to make it clear the what is called topological property. Let us consider X is equal to R with our usual Euclidean metric, and let Y is equal to 0, 1, where we have taken the trace of the usual metric on 0, 1. Let us say it as rho. Then we know that R with the usual Euclidean metric is a complete metric space, but we know that 0, 1 open interval with the usual metric rho is not complete. So, completeness is not a topological property, because we know that 0, 1 open interval and R, these two are homeomorphic, what we have already studied. Now, we give the example of topological property. Both T1ness and Hausdorffness are topological property. Proof: let X and Y be two topological spaces and F from X to Y be a homeomorphism, and let us consider X be T1. We have to prove that Y is also T1. So, to prove T1ness of Y, we have to show that every finite set in Y is closed. Let F be a finite set in Y. Now, consider the set small f inverse capital F. Since f is small f is injective, then F inverse of capital F is also a finite set, and its cardinality is equal to cardinality of F. Therefore, capital F is closed in Y as F inverse capital F is closed in X. Hence, Y is T1. Next, we shall prove that Hausdorffness are topological property. So, let X and Y be two topological space and X be Hausdorff. We have to prove that Y is also Hausdorff. So, for this, let us take two distinct points X and Y in capital Y. Then there exist unique pre-images of X and Y. Let us consider U and V are unique pre-images of n x and y respectively in capital X. So, we have to find two disjoint open sets U and V in Y such that U contains X and V contains Y. Now, since X is Hausdorff and U and V are different point in capital X, then there exist disjoint open sets U and V in capital X such that small u is contained in capital U and small v is contained in capital V, and capital U and capital V are disjoint. Now, since F is a bijective mapping, then F of U and F of V also disjoint. Again, as F is open, then F of U and F of V both are open sets. Now, these open sets contains respectively X and Y, hence Y is Hausdorff. So, next we will prove a lemma which will be useful for us. By a disk in R2, we shall mean any space homeomorphic to the closed unit disk in R2. That means a closed rectangle is also a disk. That means we will consider closed rectangle or closed square or a closed triangle all as disk. Now, if A is a disk and if H from A to D is a homeomorphism, then H inverse S1, where S1 is the boundary of D, called the unit circle, is called the boundary of A and will be denoted by partial of A. So, our theorem is any homeomorphism from the boundary of a disk to itself can be extended to a homeomorphism of the whole disk. Its proof is given in this. It is easy, we are omitting this. Now, we are considering another example, another interesting example for which we will require the finite product. We have already studied the finite product in our previous discussions. We will present here that S1 Cartesian product 0 infinity will be homeomorphic with the punctured plane, where S1 is the unit circle and 0 1 is induced with the subspace topology. We define a mapping from S1 to 0 infinity by f of theta r is equal to r cos theta r sin theta. This is 1 to 1 and onto. Since each point in R2 other than the origin has unique polar coordinates theta r. To see that f is a homeomorphism, just observe that it takes a basic open set of the form u cross v, where u is an open interval theta 0 to theta 1 and v is an open interval r0 to r1 of values r, to an open polar rectangle, and such rectangles form a basis for the topology on R2 minus 0. As a subspace of R2, by restricting f to a product of S1 cross closed interval AB for 0 less than A less than B, we obtain a homeomorphism from this product to a closed annular region in R2, the region between two concentric circles, which is described in the following example, following pictures. We end our discussion with the following theorem, following observation. That means we have told it as no Cantor-Bendiction theorem for topological space. We know that Cantor-Bendiction theorem says that if X and Y are two non-empty sets such that there exists an injective mapping from X to Y and Y to X, another injective mapping, then X and Y are of same cardinality. But similar type of theorem does not hold for topological spaces. For example, we already know that there exists an injective mapping from R to close interval 0 1, and also an injective mapping we can find from close interval 0 1 to R, which is the inclusion mapping, but close interval 0 1 and R are not homeomorphic. With this we end the discussion on homeomorphisms. Now let us pass to the next module.